Hello everyone, and welcome to the second lecture of our course, Reliable Simulation in the Mechanics of Materials and Structures. Today, we will talk about the kinematics and also about the small strains assumption, and we see its effect on the reliability of our numerical model. Let me start by some general topics. So in engineering, or many engineering problems can be modeled or treated on different scales. This depends on many factors like what kind of materials we are dealing with, what kind of structure, how big the structure that we have, what is the computational capacity that we have, and also what is our experience. So let's take, for instance, the metal forming via flat rolling. In this example, we have some kind of metal block or metal sheet which is subjected to rolling. And if we look at this material on different scales, for instance, at the atomic scale, we can see the atomic structure of this material. And we can model this problem actually on the nanoscale using the molecular dynamics. This is, however, almost impossible if we have large samples, like maybe few millimeters or to few centimeters, because then we will have to deal with tens of millions of degrees of freedom, and even supercomputers cannot do these simulations like in an efficient way. Now, if we move to a higher scale, for instance, at the micro scale, we have to recognize or consider the granular structure of our materials and the boundaries between these grains. So many researchers go for the micro models because it's also giving very good results. It's close to the physics of the material. However, it has also a problem with the computational cost, because if we have a bigger problem, then we have to deal with millions of grains, and this is not possible. So if we have like a sheet of metal or a problem which has dimensions few centimeters to few meters maybe, then we have to go for a higher scale, so for continuum mechanical model, where we don't care about the micro or atomic structure of our materials, but we have to deal with a homogenized medium. We can also include the information from lower scale in our continuum scale through multi-scale approaches. In this case, we have to solve, for instance, a representative volume element at each cost point of our finite element continuum model, and then we can include this information. This is, however, beyond the scope of this course. In this course, we will focus on continuum mechanical approach and the challenges and the numerical aspects related to such kind of models. So let me just give you like basic notations, the way we write scalars, tensors, and so on. So if we see small letters like this one here, which have no underline and they are not bold, whatever, they are scalar quantities. They could be the material parameters, they could be any constants. If we have vectors, for instance, vectorial quantities, which are first order tensors, then they have small letters with like underline below this, and this is the vectorial quantities. If we have second order tensors like matrices of this form, so we have these here, the matrix, the coefficients here, and here's a basis. In this case, these are second order tensors. We have for these kind of tensorial quantities like capital letters with underline, so and this is, as I said, second order. If we have higher order tensors, like for instance, third order or fourth order or even higher, then we have capital letters with underline, and we write on the top of this letter like n, and this is the order of our tensor. So if n equal to 4, for instance, this might be for the elasticity tensor. If we have n equal to 2, then we have the second order tensor, so we don't write the 2 in this case, simply because most of the tensors that we are dealing with are second order tensors, so we don't write these 2 very often. If you take like a printout or a script from our group or our institute, then you will see such kind of notations. The scalar quantity is similar to what we write in our hand. And for the vectorial or for the second order tensors, we don't write this underline. we use the bold letters. This is possible when you use computer, but with your hand, it will be like not easy or not possible. So let's go on to the real topic. So we will talk a little bit about the kinematics. In this context, I am recalling some of the aspects that you have learned in the continuum mechanic course, and I will discuss the different issues in connection with the reliability of the model, of the continuum model, on which which relies on these kinematic formulations. So kinematics, as you know, it's concerned with the description of the motion of the and deformation. So I assume many of you are familiar with these figures. Consider a certain continuum body subjected to an external load F0. This is at T0 at the reference or initial configuration where this body is not yet deformed. And we could have like a line element, we could have surface element or volume element belonging to this reference configuration. And then after the deformation, so at time t, due to the application of F, we'll have rotations, we have transformation, and we have deformation inside the material itself. In this case, each material point, P, can follow its own motion function. We call this xi. It's a function of x, and so the position vector and t, and it refers from the reference configuration to any current configuration, so or deformed configuration, so that we have the position vector in the current configuration, which is a small x. It's a function of xi, and this is a capital Xt. Or we can define also the capital X, which is the position vector in the reference configuration. And of course, you can switch between the position vector in the current configuration and reference configuration through the inverse of xi. In this case, the Jacobian, which is the determinant of partial derivative of xi with respect to capital X, should be non-equal to 0. So as I said, small x and capital X refer to position vectors in the current and reference configurations. And these are our starting point. Once we have this vector, then we can define also our displacement vector, u, which is small x minus capital X. Then the velocity vector, which is the first time derivative, so partial derivative of u with respect to the time. And then we have the acceleration vector, which is the second time derivative. So these kinematic quantities will be needed later, for instance, to formulate the strain, to formulate also the balance equations. A very important and crucial quantity in the kinematic description is the material deformation gradient F. And F can be defined as the partial derivative of small x with respect to the capital X. So, and we have seen that the small x is capital X plus displacement u. So by some reformulation, it will be identity plus gradient of u. And you see that for I is the identity tensor, and this gradient, it has capital G because it refers to the reference configuration. So it's a gradient with respect to capital X. If we have another gradient with small g, which is referring to the current configuration, then we take usually small g. If we have undeformed state, it means if u equal to 0, apparently f would be equal to identity tensor. Now, F includes all the information related to the rotation of our body, the transformation, and also the deformation inside the material itself. However, the rotations, they don't contribute to the strain. So if you have a certain body and just rotate it, rigid body rotation, there will be no strains or stresses inside this body. So we would like usually to get rid of these deformation or these rotations in order to formulate our strain tensor. Therefore, F can be split into a proper orthogonal rotation tensor R and a right or left stretch tensor, which includes the deformation inside the material. This right or material stretch tensor is called U because it refers to the reference configuration. And V is the left or spatial stretch tensor because it refers to the current configuration. This split can look like this. So F equals to R multiplied by U or V multiplied by R. Of course, R is a rotation matrix. It fulfills certain like restrictions and conditions. For instance, the orthogonality condition requires that R multiplied by R transpose equals to R transpose multiplied by R, and this is the identity. So this is a very important relationship which we'll use later in the formulation of our deformation tensors and also the strain tensors, which are the aim of our discussion. First, let's go for the right and left Cauchy-Green deformation tensors C and B. So you see here C equals to F transpose F, and we have seen that F transpose F will give us at some position R transpose R or R transpose. So we will use this here. F transpose F would give us U multiplied by U because R will disappear here. So and this equals to U square. And this C or the right Cauchy-Green deformation tensor is associated with a reference configuration. And the other one, so the counterpart would be then the left Cauchy-Green deformation tensor B, which is now F transpose, and this is V square, and this is associated with the current configuration because it mainly includes the information of the current state of deformation, and the other one is it has information for the reference state. So more details would be, of course, in the context of the course of continuum mechanics, where we'll define, we'll go in much more details. But here I'm just recalling some of the information which will be used later. As our aim in this discussion is to get the strain tensor, which is, for instance, the green Lagrangian or material strain tensor. So as we write here material, it means it's referring to the reference configuration. So green Lagrangian strain tensor, we write this as E equals to half multiplied by F transpose F minus identity. However, F transpose F, we have seen this, it's C, the right Cauchy-Green deformation tensor, C. And this is in the reference configuration because C is in the reference configuration. The other strain quantity, which refers to the current configuration, is the Almanzian, or it's called spatial strain tensor, and it's defined in somehow similar way. It's half multiplied by identity minus B minus 1. And as I said, it's in the current configuration. So these are strain quantities within the large deformation description. This is because we distinguish between the reference configuration and the current configuration. So the undeformed body and the deformed body in our formulation. And as you will see later, this includes nonlinear terms. And for some special cases, it can be linearized to get the linearized strain tensor. And this is the next step. So we will go for small strains assumption. And this is you'll see here. So under the assumption that the deformations are small, the norm of the displacement, so U is a vector, so in order to get a number and see it's small, we have to take the norm. This norm should be small. In this case, the gradient of B, the gradient of U, or if we take the norm of the gradient of U, would be even smaller value than U. And in the nonlinear strain formulation, we will get a gradient U multiplied by gradient U transpose. And this is then a very much smaller number, and this can be neglected. Remember, our starting point in this argument is that U is small. So if U is not small, then the whole argument will not be valid. Just for illustration, assume that the norm of gradient of U is 10 to the power of minus 3. In this case, the gradient of U transpose If we take the norm of this, will give us even smaller number. It would be 10 minus 6. It's much smaller, so it could be negligible. For instance, if the gradient of u give us a higher value like 1, then if we take the gradient u transpose, then it would be again 1, which is a considerably large number, and we cannot neglect this. Now, just to show where these terms show off, let's recall the definition of f. So f, as we talked like a few slides ago, it was the identity plus the gradient of u. Now, if we take the transpose of f, identity would be the same, and then we have gradient of u transpose. Now, if we plug this in the definition of the strain tensor, so the Green-Lagrangian strain tensor, it will give us half multiplied by gradient of u plus gradient of u transpose plus gradient of u transpose gradient of u, and this is our nonlinear term, this one. Now, it would be negligible if we have small deformation, and this is the assumption that we'll proceed from. So let's now summarize this. So if we have linear or linearized strain, so we simply linearize E, so we write E lin equals to epsilon equals to half multiplied by gradient of u plus gradient of u transpose. And this is, and if we have a small strain, then we don't really distinguish between the reference configuration and the current configuration. So that's why we could write also gradient of u in capital G or small g. It would not make any difference. Notice that we call this equation as double star, and the equation which was before in the previous slide, it's 1 star. So we are going to use these equations again in our later discussion. Just to have more feeling about the importance of these nonlinear terms and the possible errors that could happen if we assume small strains in some improper way. So we compare now between E and epsilon. Assume like a very simple example. We have a bar here. It's a one-dimensional structure, which is constrained from the bottom, and we apply a load at the top of it. Initially, this bar has a length of L0, and through elongation, so the deformation, it will have a new length, which is L. Let's say the end-deformed state, it's associated with T0, it's our reference configuration, and then after deformation, it's time T, so it's the current configuration. And the task here to compare between E and epsilon, so the Green-Lagrangian strain, which includes nonlinear term, and epsilon, which is a linearized strain quantity. And this conversion will be carried out for 2 cases. So assume that the length is 1 meter, and the length after elongation, it's 1.05, so we have 5 centimeter elongation. And for the second case, L0 is 1 meter, and after elongation, it would be 2 meters. So for the solution, of course, we have here a problem in one-dimensional space, so we don't really need to take care about the if it's like vectorial or tensorial. So all the quantities in this context would be then scalar quantities. So that's why we don't write we don't write the underline below the letters. So we drop this from all the following samples. And so assume the bar to be a line element. It means L0 would be D capital X. So our line element in the reference configuration, and L equals to D small x, which is our line element in the current configuration. Now we recall the definition of f, our deformation gradient, dx to d capital X, and then it will be L divided by L0, and this is also f transpose, so the transpose would be exactly the same. Now, if we plug this information in both E and the linearized E, so the epsilon, which is a large and small strain, you will see that E, the Green-Lagrangian strain, will be half multiplied by L square minus L0 divided by L0, and the epsilon would be then L minus L0 divided by L0, and this is delta L divided by L0. So epsilon is called also the engineering strain, which is widely used. If we reformulate this, we see that E, our green Lagrangian strain, includes the small strain, so epsilon, and it includes a nonlinear term, which is half epsilon squared, and this is the higher order term, and this is what we usually neglect if we say no, our strain is linear, so we can simplify our formulation. And of course, you should be aware that if you want to consider this nonlinear term, it means your description is more accurate. However, it increases the computational demand to a large extent, so that people prefer not to use this. So it's just to increase the speed of your computation, people go for this simplification assumption. Now let's plug in the values of L and L0 to estimate the errors. So for the first case, when we have initially L0 equal to 1 meter and we have elongation of 5 centimeter, we see that capital E and epsilon, they are very close to each other. So the difference here would be 1 to 5 after the third number after the comma. And then if we compute if you compute the errors, so L1 error, this way we see that we have an error of 2.44%, which is a very small error, and this is negligible. So I would say for this small deformation, we can use epsilon later, and we can now accelerate our computation. Now, if we take the second case, where initially the bar was 1 meter and became afterwards 2 meters, we see that E is 1.5 and epsilon equals to 1. In this case, the errors are really high. So you see, we use the error in similar way. We can compute this, and it would be 33%, which is a very high error. So if we go for an assumption of small strain in this case, then we are doing a big mistake. So you should be very careful in this context. Now I will I illustrate in this figure like different strain quantities. For instance, this one here, epsilon is L minus L0 divided by L0. This is our linearized strain or engineering strain. And you see it's line, so it's a green line here. The one which is highlighted here, it is our green Lagrangian strain. You see it's nonlinear, it has this, this shape here. And we have other strain quantities, because the strain is dimensionless quantity. It's proposed just to have to formulate later the energy functional. So it's something that you cannot measure directly from the experiment or from the observation. So we have, for instance, the Almanzian strain. If we apply this to our bar problem, it will look like this. And we have other types of strains. For instance, the logarithmic strain, so logarithm of L divided by L0. So you have different kinds of strains. And now, as an engineer, when you select or decide what kind of strain I'm going to use to solve a certain boundary value problem, you should be aware of what kind of deformations you have. So if your deformations are in small range, so let's say here, by the way, f-axis is our deformation gradient, and y-axis is our strain measure. So if you have small deformations, let's say between 1 to square root of 3 to square root of 3, then we can use any of these strains quantities. It will not make big difference. Maybe we'll go for the linearized strain because this will make our computation faster. However, we should, if we have large deformations, then we have to look at the extreme state of our of the deformations. So if we go for infinite stretching, so if you have a bar and you are stretching this to a very large extent, as the stretching go to some kind of infinite values, so in this case, this axis will go to the left, sorry, to the right. If the stretch is getting to infinity, then your strain quantity should also capture this effect. And you see here that the Almanzian strain, in this case, will converge to a value of 1 to half. It means it cannot capture this effect. The linearized strain can capture this. The logarithmic strain can capture this, But for instance, also the green Lagrangian strain will capture this, but it also will converge to a certain value, so it will not be like very much suitable. If we go for full compression, so if you have a material and you are compressing this to a certain material point, so in other words, your F is getting close to 0, you see some strain measures like green Lagrangian, it will end up by -½ so it will not capture this full compression, because this also should be, or the strain should also converge to -∞ if we have infinite compression. And we see that the linearized strain also will, it has a minimum value of -1, but the other strain quantities like the Almanzian or the logarithmic will capture this convergence to -∞, so they would be suitable in this case. So it's important to understand the problem that you are dealing with, the range of deformation in the selection of the strain quantity. The difference between small strains and large strains, it's under the category of geometrical nonlinear problem. But in solving initial boundary value problem, we have other sources of nonlinearities. So two main categories are the material nonlinearity. In this case, it's about the relationship between the strain and the stress. So linear elasticity, it means we have a line between epsilon and sigma, as you see in this figure. And nonlinearity would be then we have like a polynomial shape for the relationship, or if we have other types of deformation like the elasto-viscoplasticity, in this case, we'd have other curves here. So it's also nonlinear. The other kind of nonlinearity would be the geometrical nonlinearity. And in this case, we have to capture the change of the geometry as we have to consider this in our mechanical formulation during the computation. And this is what we are dealing with in the context of large deformations. For example, if we have, as I said, large or finite deformations, and by the way, large or finite deformation could also be associated with small or large strains. So you could have like large displacements, but small strains. I will give an example to this. If we assume we have a thin wall structure under pure bending, so we have a structure like this, and you are bending this, it's clear, we can see in our eyes that we have large deformation. So this point become here. However, if we measure the strains, or let's say the maximum values of the strain for a point here, it will be so the maximum values of the strain, it will be TB divided by L2. It's for this pure bending. And if we consider that our thin wall structure, it has a length of 500 centimeters, so it has 5 meters. It has a thickness of 10 centimeters. Then our strain measure, it will be 3%, so 0.03, which is much smaller than 1. And this is a small strain. However, the deformation or the displacements are high. In this case, we have also to go for finite strain theory in the kinematic formulation, and we have to consider the deformed geometry during loading. Like final remark in this video would be, it's important to distinguish between the volumetric and deviatoric part of our strain measure. I'm introducing this here because we will need this later in our FlexPDE code and also the formulation of our strain tensor maybe in the next lecture. So having this strain tensor as epsilon ij, and this is EI dyadic ETA, our basis vector. And if we have three-dimensional settings, then this I and j, they change between 1 and 3. And if we have I equal to j, then we have normal strains, as we see in this figure. And if I does not equal to j, these are the shear strains. Now we can really split the volumetric deformations or the volumetric part of the strain from the deviatoric or pure shear part. So the volumetric part can be derived using the trace operator. And this is E, trace of epsilon. So this is a scalar quantity. And we simply sum up the diagonal entities of our strain tensor. It would be then epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3. And for illustration, you can see here the yellow geometry represents the body before the deformation, and the red ones represent after the volumetric deformation, pure deformation, would be if you have expansion. So if you have a body and we put it in the temperature, it will expand. And this is the compression. So if we take, for instance, a certain body and put it in water, it will have somehow uniform pressure on the boundaries, and it will there will be shrinkage or will be pure compression. And for the isochoric or deviatoric deformation, we simply take the deviatoric of the strain. So it's the total strain minus the volumetric contribution, and what remains is simply the pure or shear contribution. So as you see here in simple shear, as an example, you have only the deviatoric, or it's called also the isochoric deformation. So with this, I'm at the end of this video. Thank you so much for your attention, and we see each other in the lecture on Monday. Thank you so much.